So we are talking about the normal distribution and the empirical rule, assignment number 31 in our Google Classroom. If you click on the notes, uh, we're beginning this section now on inferential statistics. And our previous sections have focused mainly on describing the data, what its shape is, what its average is, how it's distributed, how it's spread out, if it's skewed left or right. All of that is part of a section of statistics called descriptive statistics. And now we're getting into inferential statistics, where we use data to infer or predict the probability of something. So this is a picture of the normal distribution. Notice it's got this bell-shaped curve. It's nice and symmetric. There are other distributions, the binomial distribution, the chi-square distribution. All of those have their different characteristic shapes. Okay, but this is the first one we're going to look at, and probably one of the more common distributions in beginning statistics. So a couple things about this. When we say, when you see this little U-looking thing, this is the Greek letter mu, and it signifies the mean. And this little O with a hat on it, this is the Greek letter sigma, and it means the standard deviation. Okay, so on a normal distribution, the mean is at the center, or mu is at the center, and we section it off into sections based on how far away from the mean they are in terms of standard deviation. So this would be 1 standard deviation above the mean. This point is 2 standard deviations above the mean, and this point is 3 standard deviations of the mean. And each of those cordons off a section of the curve, and the total area underneath the curve is, of course, 100%. Okay, if you add up all the areas out here to infinity, notice ours only goes up to 3 sigma and negative 3 sigma. But if you kept going on out to infinity, the total area would be 100%. So if you're at the middle, the total area to the right of it is 50%. The total area to the left is 50%, which makes up 100%. So the empirical rule says that 68% of the data lies within 1 sigma or 1 standard deviation of the mean. So what does that mean? Well, that means if you go 1 standard deviation above, then 34% of the data is between the mean and 1 standard deviation above. Then if you go 1 standard deviation below the mean, then 34% of the data, another 34% of the data would be between the mean and that. And if you add those two together, you get 68%. If you go up another standard deviation to 2 standard deviations, you get a further 13.5% to the right, a further 13.5% to the left. And if you add up all 4 of these sections, the green, the 2 purples, and the other green, that would give you 95%. So 95% of the data is within 2 standard deviations. And then finally, 99.7, or pretty close to 100, that's why we say 68, 95, 100, is within 3 standard deviations. Now, if you're getting more precise and you're talking about manufacturing and precision manufacturing, then you want to say 99.7, and you would go out to 4 sigma, 5 sigma, even 6 sigma, which means a very tight controlled process. 6 sigma is also a certification in business. But you can keep going out 7 sigma, 8 sigma, you would get even more, even closer to 100%. But for our purposes in beginning statistics, 3 sigma is pretty close to 100%. Okay. All right, so some thoughts. So what percent is below 1 standard deviation above the mean? So if we go to 1 standard deviation above the mean, that is right here. Okay. And then if we're talking about what percent is below that, so you go, we got this 34 that's here, at 34%. So 0.34 plus, well, from the mean on down, we know that's 50%. So 0.5 for 50%. That equals 84%. And notice I'm saying percent, but you're saying, Mr. Keller, you're typing 0.84. Well, if you translate 84%, that's 84 over 100. That would be 0.84. So start thinking about these decimals as being equivalent to a percent. 0.34 is 34%, 0.5 is 50%, 0.84 is 84%. All right, next. What percent is above 2 sigma below the mean? So if we go to 2 sigma, this is 1. 2 sigma below the mean is there. So we want everything that's above that. So that would be 13.5% plus 34% plus, so that's these two sections, plus the rest of it, which is 50%, which equals 97.5% if we add those up. So 95% is above the mean, above 2 sigma, or you have a 97.5% chance or 97.5% probability of getting a value above 2 standard deviations below the mean. Okay. All right, next question. If a normal distribution, now in a standard normal distribution, the mean is 0 and the standard deviation is 1. So this would be 1, 2, 3. And this would be -1, -2, -3 in a standard normal distribution. But if we don't have a standard normal distribution, which is possible, and it has a mean of 10 and a standard deviation of 2.3, what percent of the data is between 7.7 and 12.3? Well, we can label our bell curve like this. Put the mean at the center, and then add 2.3 going up. So this would be plus 2.3 would be 12.3, plus another 2.3 would be 14.6, plus another 2.3 would be 16.9. And then going down, we just subtract. So 10 minus 2.3 is 7.7, minus 2.3 is 5.4, minus 2.3 is 3.1%. Okay, so we're asking what percent of the data is between 7.7 and 12.3? So between here and here. Okay, well, that's 34% plus 34%, which is 68%. Okay, so effectively they're asking what percent of the data is within 1 standard deviation of the mean, and that's 68%. So remember, 68, 95, 100 rule. 68, 95, if you want to be more exact, 99.7. Okay, so let's go look at an activity for this. So if we open up our activity here, little empirical rule activity. All right, so we're looking at this. This is our data. It's already been sorted in order, but if you wanted to do that yourself, click on the column, go to Data, Sort Range. Data has a header row. That means it has a title above all the data. Ours does. So select that. Notice it automatically changes the sort by to the column name there. And A to Z means ascending from smallest to largest. Z to A means largest to smallest. So we want smallest to largest. Sort. And boom. Nothing changed because ours was already sorted. All right, so we want to find the mean. So here in cell L3, we're going to put the mean. We know how to find that. Equals average. And we want to select all our data. There we go. A2 to A40. Boom. That's the mean. And then we want the standard deviation population. So equals stdev.p. And then again, select the range, A2 to A40. And let's just round that down a little bit to make it a little bit more palatable. Of course, Excel remembers the exact value. Okay, so that's there, 13.03 plus 16. So our mean is 13.03, and our standard deviation is 16.7. So it says label the normal curve up to 3 standard deviation. Well, here's our normal curve. Notice it's a standard normal curve, 0, and then 1, 2, 3, and the negative 1. We're going to adjust it. We're going to label it for our distribution. So 13.03 is here at the center. So let's put equals, and let's just select L3. Boom. All right, and then this one is 1 standard deviation above, so equals, well, that's the mean plus 1 standard deviation, L4. Boom. 2 standard deviations would be equals the mean plus, now we want to do 2 of those, so 2, and then we use the star, which is above the 8 key. Star means multiply, so 2 times L4. And then the same thing for 3, so that would be equals L3 plus 3 star L4. Boom. So there we are labeled that way. And then if we want to go the other way, it would be L3 minus L4 because we're going down. And then equals L3 minus 2 times sigma. And then finally equals L3 minus 3 times the sigma, L4. Boom. So there is our standard normal distribution curve labeled. Now, obviously, how many hours a week? You wouldn't have negative hours. So this whole left side of this graph doesn't quite make sense. Doesn't make sense in our for our data set. Okay, because our data set isn't a continuous number line all the way to including negatives. But we can check a few things. How many data points are within 1 standard deviation of the mean? Well, what that means is how many data points are between negative 3.75 and 29.80. Okay, so if we look here, 0 all the way up to 28. So if we look at that, that count there is 34 data points. So 34. And then it says what percentage is that? So that would be 34 equals 34 divided by the total. Well, there's 39 data points, even though there's 40 cells here. The top one is the title header, so you take off 1, so 39. Okay, so 87%. Well, does 87% really fit our empirical rule? It should be 68%, so doesn't fit empirical rule. Okay, for 68%. All right, next one. Within 2 standard deviations. So that would be between negative 20 and 46.57. So let's look all the way up here to 42. Well, that's 36 data points are within 2 standard deviations, which is equals 36 divided by 39. That's 92. That's pretty close to empirical rule for 95%. That's pretty close. Closer than the other one was. All right, and let's look at within 3 standard deviations. So that would be from negative 37 to 63.34. And that pretty much gets us everything except for the last one. So that's 38. So equals 38 divided by 39. So 97%, that's also close to the empirical rule for 99.7%. Okay. Again, closer than the first one. So the next question, does this data set appear to fit a normal curve? And this is kind of a judgment call. Okay. At least based on the empirical rule, one of these doesn't. The other two do. So you might say maybe. Two of the ranges fit or are close. Okay, you could say no based on the first one. It doesn't really fit. You'd have to really go through some other tests. We have done Pearson's second coefficient for skewness, so that would check the shape of the curve to see if it's close to being symmetric, like a normal distribution should be. And if it's between negative 0.5 and positive 0.5, then it's pretty close. But just looking at the number of data points that are within there, it's really not clear if this is close to a normal curve or a normal distribution. Okay. Next, what range of hours does a typical student at NHS spend with family? What data backs that up? Well, if we're looking at our normal curve, we could say anything from 13.03 to up to 29.80. That would give us about 34% of the data there. If you went up to 46.57, that would give you more of the data, almost 40-something% or more of it. So it's kind of a judgment call. You could kind of base it here and make a histogram and look to see where this sample is, and then use that to infer about the larger. But it's a little bit safer here to look at this. So normal curve. So what range of hours does a typical 13 to 29 would be a pretty safe bet. It would probably get you the greatest range or highest likelihood, 34% of people responding. If you wanted to increase that, you could say 13 to 46. And that would give you a good chunk of the data in terms of probability. 13 to 46, because that's 2 standard deviations. That would give you almost everything. 95, if you wanted to be even more precise, you could go up to 63. All right.